computer. Okay, we're being recorded now, so be careful. Anyway, so again, what we're going to be doing this week is we have homework due on Thursday night. We have our exam. I'm going to mute everybody real quick, and then you can unmute yourself. There we go. We have our exam on Friday. It's over chapters 14 and 15 only, so it's all benzene and benzene-related materials. Our Zoom project is Thursday afternoon, and it's going to be like ortho-para direction and order of reagents. So, hey, I want to make this isomer. If I made it in this order, what would it make? If I made it in this order, what would it make? And so that's what our activity will be tomorrow afternoon. And then, of course, I will, you can email me. I've had Zoom office hours with several students already. So that is still also available to you if you want, individual, questions answered. Okay. So that being said, that takes care of all our administration for now. So let's go ahead and continue on with the chapter 15. Okay. And we were talking about ortho-para direction and whether or not a substituent activates or deactivates our reactions with benzene. Okay. Share. All right. Everybody should be able to see my screen, I hope. If not, go ahead and ping me in the chat there. Okay, I put on this side, I have the gallery view so I can look for waving. Okay, so we talked about ortho-para direction, and one of the ways I told you to look for ortho-para directors and or activation is looking at all of these have the ability they have a lone pair to contribute into the ring to pull resonance, a resonance cation out of the ring, giving us that fourth resonance contributor. Therefore, if we can form that fourth resonance contributor, we will activate the system, okay? Now, the halogens and the alkyl groups are weakly activating because they can stabilize that a little bit, but there's not a very strong inductive effect because that's a non-polar carbon-carbon bond. And the halogens deactivate slightly because of the inductive effect, but because of the conjugative effect of those lone pairs, they can direct ortho-para. And all of these meta-directors are what we're going to talk about today and why they meta-direct and why they're deactivators, okay? So let's move on to our deactivating. And so we're going to look at that same thing about that resonance intermediate formed and how many resonance contributors we have. And not only that, but where that cation resides on the ring. Because where that cation resides on the ring tells us why it's the meta-director, because of where that positive charge is and where that positive charge is in proximity to either a positive charge or a partially charged substituent, okay? So if we look at our system here, we have our, we're going to do a CF3 right here. And so basically we have 3 fluorines pulling electron density away from the carbon, making that carbon a net partially positive, and therefore it is pulling electron density out of the ring, okay? So that means there's less pi electrons already to go out, reach out and grab at that electrophile, that positive charge, okay? So just inherently not having as much electron density above and below that plane of the benzene ring is making it so that, I'm going to be lazy about going out and reaching out for a nucleophile, okay? So that's our first step of our inherent deactivation, okay? So now let's talk about the resonance effects and why it directs things, okay? So if we were to attack, if we were to have our electron-neutron group here, and think of all of our electronic group as at least partially positive and not full positive, and it reaches out and grabs that at the ortho position, that gives us our cation in the position right next to where our hybridization changed from sp2, from an sp2 hybridized center to an sp3 hybridized center. And we now have that carbocation still in an sp2 hybridized orbital. Okay. Now, because it's in that p orbital, we have the ability to have resonance contributors. So we can move our electrons over here, which moves our positive charge here. And if we move these electrons over one more, we'll end up with our positive charge here. Now, this particular contributor is more unstable because this has a partially positive charge. And so we have a positive charge being repelled by another partially positive charge. That's why it's the most unstable of the contributors. Okay? So the same is true if we have attack at that parasite, because the site that is para, not a parasite, sorry. If we have the electrons come out and grab here, we're going to end up with our first positive charge in that position there. And by resonance contribution, we're going to end up with that positive charge next to our partially positive substituent. And then it has to go back and move away from that partially positive substituent, meaning that this is also a highly unstable contributor because we have a positive charge next to a positive or partially positive charge, giving us a repulsive effect, meaning it's less stable than the other two contributors. Okay, so in both of these cases, instead of having 3 or 4 contributors helping stabilize that charge, we now have 2 that are about the same and 1 for each of those that is less stable. Okay, so just that alone tells us, number one, we have fewer resonance contributors that are stabilized. And 2, that's another reason why we're starting to deactivate the system, because it doesn't want to, because of that electronic drawing. Okay. Now, this problem of having this unstable resonance contributor here is minimized when we attack in the meta position. And that's because by resonance, that positive charge is never on the carbon adjacent to our electron withdrawing group. Okay, so in the case of our meta attack here, we form our positive charge here on the carbon adjacent to the one that has that positive charge, that electron withdrawing group on it. Okay, so as we resonance contribute all the way around the ring, it never has that positive charge, that carbocation, on that carbon with our withdrawing group. Therefore, all 3 resonance contributors are equal, and therefore it is more stable overall than either of the other 2 attacks. Okay, so this is, I think, the best way to understand why it's meta-directing, and just the whole concept of electron withdrawing away from that pi cloud is why it's deactivating. So between those 2 concepts there, we can now look at our table again and look at our donators and our withdrawers here and say, okay, I have an idea of why they're meta-directors or why they're ortho-para-directors. I also have an idea of why they're activators and why they're strong activators or weak activators. Weakly deactivating, but still ortho-para direction. Okay, so again, these electrons can contribute to that 4th resonance stabilized structure. These have some of their electron density being pulled away by the carbonyl. These only have slight activation because that's a non-polar bond. And these are only ortho-para direction because of the lone pairs. All of these have either a partially positive or a full formal positive charge on the atom directly attached to the benzene ring. Okay, so using those arguments, I think we can safely say that we can predict ortho and para direction based on what the structure is. We don't have to memorize the cable. We can look at the compound and say, it will probably be an ortho-para director, or it will probably be a meta director. Okay. So now let's summarize that in moving to our next thing. Okay. So we can put this on a spectrum of activity versus ortho and meta directors, okay? So if we look at the entire spectrum, as we move to an electronegative atom with a, if we compare the electronegativity and the availability of our lone pairs, we can actually see ones that are more activating or increase the activation even more. So in the case of this, we have an electronegativity difference between the nitrogen and the oxygen, okay? So nitrogen is just a little less electronegative than oxygen, but that oxygen has 2 lone pairs available to it. So the reason that our amines here are just slightly higher in activation has everything to do with it's a slightly less electronegative, okay? But these oxygens are activators because it has 2 sets of lone pairs, okay? Now, our amides here, because of that slight withdrawing from that carbonyl compound here, that gives us our lowest level of activation for a heteroatom, okay? And then, of course, the carbon is a slightly activating due to that hyperconjugation, okay? So at that band right there is where we say, okay, everything above that line is an activating group, and it's either inductive or lone pairs, okay? So because of our electronegativity difference, these are starting to have that inductive effect take place, meaning it's no longer activating. But because of the conjugative effect, it still directs orthopara. So that makes everything above this line an orthopara director, okay? Because that availability of that 4th resonance stabilized intermediate. Okay, so then everything else is decreasing, and it's decreasing by level of partially positive charge, okay? So in the case of our aldehyde, because the hydrogen doesn't have any electron density to donate back to it, it's the least deactivating of the system. Then as we have carbon here, that is the electronegativity difference between the 2 carbons is the same, so that the carbonyl is taking the full brunt of its partially positive charge. Then we have donating groups, then cyano, nitro. And in both of these, if we looked at our formal charge, we have a positive charge on the sulfur and a positive charge on the nitrogen. And then, of course, this is a full positive charge on nitrogen as well. So that increases the activity as we go, okay? And all deactivating groups like this are meta-directors as well. Okay, so this kind of sums up that whole concept in a bow. Now let's utilize this to our advantage. Okay. So, all right, so when we have an orthopara director, we have a product ratio possible for us, okay? So statistically, we have 2 ortho positions and 1 para position, right? So statistically, if our group that was donating electron density or allowing us to have that 4th resonance stabilized cation, we should get twice as much ortho substitution as para substitution because of, well, you can hit here, here, or here, and that's how they're different. However, at some point, sterics of the group that's already substituted there will start to take hold. So our product ratio will change based on the size of that group in the benzene ring. Okay. So let's take something nice and small, and then we start increasing it and decreasing it, okay? So let's take toluene, okay? It's just that methyl group there. And when we think about sterics, when we were talking about primary and when we were talking about attacks with SN1 and SN2, sterics was one of those driving factors. Going from that primary to the secondary to the tertiary changed our reactivity, okay? We're gonna see that effect take place in our product ratios in these benzene rings, okay? So if we look at toluene here, okay, our methyl group is pretty small. It's one of our smallest alkyl groups, and so we'll use that as our small right here. And when we nitrate this, we find out that we get 61% of it is ortho, and 40% of it is there. So that's not quite a 2-to-1 ratio, but it's getting close to that theoretical 2-to-1 ratio, okay? So just by this small group here, we're getting close to that statistical, 2 available spots here and here. And that is the exact same compound in the end. And then that 1 available stop here. Okay. Because it should be 66 to 33. So it's got a little more on that para position than it should statistically. Okay, just the addition of another methyl group right here, we've changed that product ratio again. Remember, with our methyl group and our ethyl group there, those are sp3 hybridized bonds, meaning they're sigma bonds, meaning they have free rotation. So you actually have that methyl group swinging around in free space. There's nothing stopping it, right? It's at a very small barrier of rotation. So just that little methyl group spinning around the top is now blocking 11% of the attacks at that ortho position, okay? And our product ratio goes, it changes. So we drop our number of attacks at our ortho positions down from that 66% down to 50%. And then, of course, the remaining attacks happen at the 50% or the para position, okay? Now, if we go even more, not just have that 1 methyl group spinning around, but now having 3 methyl groups there, so it doesn't matter even which orientation they're in, they're blocking attacks from that top position, okay? And we see the product ratio goes down again. Product ratio goes down to about 20%, with 80% of it happening in that 4 position or that para position, okay? So because we're not changing the electronics of the system, this effect is entirely because of sterics. Okay, so now we have to compare and contrast the effects, okay? What if you have 2 things on your benzene ring, okay? So we have to do 2 things. We have to look at each group and assign whether it's an ortho or para director, and then we have to assign each group to decide how many of which position do I have 2 things directing it to this position or only 1 thing directing this position, okay? So let's start with this and do it stepwise so that we can see how each of the contributors will give us a preferred product ratio by assigning them to the system, okay? So when we have directing effects that reinforce a substitution, then that position is almost exclusively used, okay? So for example, if we look at this compound here, we have nitrobenzene, okay? So, I'm sorry, nitrotoluene right here. So the methyl group is slightly activating and an ortho-para director. The nitro group is, I'm sorry, the methyl group is slightly activating and an ortho-para director. I hope I said that. And the nitro group is a meta-director and slightly deactivating, okay? So right off the bat, the activator and deactivator are trying to compete with each other, okay? So that's telling us that the reaction probably will happen, but now we have to figure out where it's gonna go, okay? So in the case of the methyl group, we know that that's an ortho-para director, okay? So it's gonna direct here, it'll direct here, but there's already something in that nitro position, that para position. So that means we're not gonna do a substitution there. So that means the methyl group is going to promote a substitution in those 2 ortho positions or those 1-2 positions, okay? Now, the nitro group is not promoting anything here, right here, because it's promoting meta direction, okay? So that means the nitro is going to also direct to those same 2 positions, okay? So the nitro is meta directing, and it turns out that the methyl group, which is directing ortho, and the meta director nitro group is also directing to the same carbon. That is reinforcing the idea that we're going to get substitution, and we're going to get substitution at this one and only site, okay? So if we add 1 equivalent, all right? So do we see why the nitro group is directing it to the same place the methyl group is directing it, okay? So in theory, our product ratio should be like 99 to 1. for getting it in this position because both groups are directing it to the same place. Okay? So, what if they aren't directing them to the same place? What if they are competing? Okay? So, for example, we have two different activators, okay? We have an activator with a lone pair on it. This is one of those amides we have. And we have an activator with just a weak activation, okay? So this amine group with the lone pair on it is directing ortho-para, but again, the para position's blocked, so we're not worried about that. So these two are where the amine is directing it, okay? So now if we look at our methyl group here, it's only weak deactivating, but it's also ortho-para director. The para position's blocked, so it's activating it toward these two slots here, right here. In the case of when you have activators, the more powerful activator always wins, okay? Because it has a stronger resonance contributor, therefore our major product is going to be the one ortho to the stronger activator. So knowing the relative scale of activation is important to help you predict the correct product ratio. Okay, so let's go on to a different situation. Okay, let's go on to a situation where we have conflicting or crowding results here. Okay, so the first thing I want to do is I want to look at the red methyl right here. And that red methyl is weakly activating, but it's an ortho-para director. And so the red one is going to direct here, here, and here. Okay? So those are the three sites that it's directing any substitution to. Okay? So let's look at the other methyl group. Let's look at this green methyl group now. Okay? That green methyl group is promoting ortho-para as well. So the green methyl group is promoting here, here, and here. Okay, so, but when we actually do a mono substitution, we only get one product, okay? And the reason is that even though all three sites are equally activated, this site right here has two methyl groups next to it, okay? So this site here is actually crowded out. It's activated, but you cannot get your electrophile in there to react at that position. But you say, hey, doctor, what about if it reacted there? That's the other position, right? Well, if it does react there, it actually turns out to be the exact same compound, because if we flipped the molecule over, that would be substitution, mono substitution on that same ring system. So it's actually an equivalent molecular compound. So it doesn't matter whether it attacks here or here, it's going to give us the same product. Okay. So remember symmetry. If you flip that molecule over, you'll see that that's exactly the same. Okay, so we have different possibilities for different things. We can have them work against each other. We can have them work for each other. And then we have a steric crowding possibility to get us to our correct predicted product, okay? So let's take this a little further and try to predict where we're gonna go after we've done our first addition, okay? So let's talk about anisole in particular. Anisole in particular is one of our more highly activated systems right here. And it's because it has that oxygen and it's got two lone pairs. And so in anisole, actually that methoxy group there is so activating, you can actually do this without using a ferric chloride catalyst. It is so activating, it'll reach out and polarize that bromine by itself. And you'll get a product ratio of ortho and para. And statistically, you do get the mono substitution at that activated, a little bit more at the ortho site than at the para site because of the two possible ortho additions and only one possible para position. Okay. However, the addition of the bromine does not deactivate the ring. Okay. So we have a highly activated ring, and it's not deactivated by adding the bromine to it. Okay. So when you actually add the Lewis acid catalyst to it, you can get multiple brominations. Okay. Now notice that because the bromines are orthopara directors, however, they are weakly deactivating, the methoxy directs where all the bromines go. So the methoxy is directing our first bromination, and then because that site's blocked, it'll brominate at the other two, the other ortho position and the para position. Okay. So we have activation plus direction as we go to filling out more and more of the reactions. All right, questions on that? We're all doing good. We're doing good on time. It's only 12:30, so let's continue on. All right, so let's look at other effects we have here. Okay, the other effects we have are based on the idea that our deactivating groups will not allow certain reactions to happen. So in a deactivated benzene, things like nitrations and sulfonations can happen. However, if you have a strong or moderate deactivator, Friedel-Crafts reactions do not occur. Okay, so and there's a couple different reasons for that, and we'll talk about that. So because of the sulfonation group right here, we have that positive charge on sulfur and this positive charge here. Those are strong enough deactivators to not allow for the attack of the Friedel-Crafts reagent. Yeah. So, because remember, our Friedel-Crafts reagent here has a carbocation on it, right here, after we make our complex with our aluminum chloride. Okay. So, not the alkylation nor the acylation works with nitrobenzene or sulfonic benzene. So, the first thing we have to think about there is, so if we want them both on the product at the end, we might have to change the order of our reactions because these reactions don't progress once you have those electron withdrawing groups on there.
Dr. Irvin, I had a fast question, if you could. Just to make sure I'm understanding like the mechanism of why it's an electron withdrawing group. Would you say it's because the sulfur group is like disrupting the electron density above and below the ring? Is that what's occurring?
No. What's happening, it's a pure inductive effect. So if we were to draw out our Lewis dot structure for our sulfonic acid here, and then if we were to look at its full, if we were to draw out its full formal charge, we actually would have a one of the resonance structures would have a positive charge on that sulfur. So even in all of its resonance configurations, we're going to have a partially positive sulfur there, and that is inductively pulling electrons through that sigma bond.
Okay.
And so if we looked at nitro is a little bit easier because one of the electron contributors in the Lewis acid structure is actually this, where you have that positive charge on nitrogen and the negative charge on oxygen. And so that has a strong inductive effect pulling electron density through that sigma bond. Okay, so this has a true formal plus charge. This has a partially plus charge, just like a carbonyl. Does that make sense?
A little bit more, thank you.
And the answer to the question in the chat is yes. It is basically pulling electron density away from the aromatic ring, so those electrons are less likely to need to reach out and grab something else. So there's less of that electron pillow above and below the plane to reach out. Okay, So what we've seen is that we can get these reactions to go when we have our Lewis acid catalyst, right? So in the case of just adding bromine in the dark, right, we saw that that reaction doesn't behave like a conjugated diene or a diene. We didn't get 1,2 addition, we didn't get 1,4 addition, we got no addition if we had bromine in the dark, okay? So we don't see the electrophilic substitution reaction until we put in our Lewis acid catalyst here, okay? So when we put in our Lewis acid catalyst, we get the ortho addition and the pair addition. However, if we change the mechanism such that we don't actually create that anion, we don't create that electrophile, we can undergo a different reaction, okay? So in the case of bromine in the presence of heat or light, if we generate a radical, what we're going to end up doing is we still are not going to do substitution on the benzene ring. However, we are going to do substitution on that benzylic site, that site 1 carbon away from the benzene, okay? So this is called benzylic halogenation, and this benzylic halogenation happens when we have light or peroxides or heat, okay? So as we move forward and you start looking at reactions, you look for, if it has the Lewis acid catalyst, you're substituting the ring. If you don't have a Lewis acid catalyst, is there some other radical reaction that can happen? Is there a double bond, or is there a benzylic carbon for us to substitute on, like here? So reaction conditions are going to start to play a bigger and bigger role in getting to the right product. Okay, so another thing about benzenes is that if we tried to oxidize them down like we would a regular alkene using peroxides or nitrate, or I'm sorry, chromic acids, the actual benzene ring is so stabilized by resonance that it itself is rarely attacked by that system. There's a weird situation where it does, but most of the time, if you have any alkyl group attached to that benzene ring, you know, it will oxidize down the chain, creating a carbonyl or a carboxylic acid, okay? However, the one specificity you have to have is you have to have at least one benzylic hydrogen, okay? So notice we have 1 hydrogen here and we have 3 hydrogens here on those groups there. If we have those benzylic hydrogens, that means we can oxidize that down to a carboxylic acid. Okay, so it has to start oxidizing it, giving us some kind of oxygen or an alcohol there, which then can oxidize off even carbon-carbon bonds like this isopropyl group here. Okay, so, but again, you have to have one. So that means the T-butyl group is not going to react under those conditions. Okay. Now, if you have more than one of these groups on there, there's no specificity. Once it starts oxidizing down, it's going to continue oxidizing all of your alkyl groups. So in the case of this lower example, we have diethylbenzene right here. And not only will it start oxidizing the first one because it has benzylic hydrogens to the carboxylic acid, there's no reason it's not going to oxidize the other one down to give us our dicarboxylic acid. Okay. So, but again, if you have the T-butyl group here, there's no reaction because there's no benzylic hydrogen to start the oxidation. You must have a benzylic hydrogen to allow that oxidation to progress. Okay, all right. So let's look at some other oxidations that we can do. So in the case of having something where we have a double bond or a hybridized sp or sp2 hybridized carbon next to the ring, we can still oxidize at that position, that 1 carbon out from the benzene ring, without oxidizing the ring itself. So in the case of this propylene phenyl group here, we have a benzylic hydrogen, that means that that double bond can also be oxidized, and it's going to clip off the chain and oxidize all the way down to the carboxylic acid. Okay, in all the products of this are all the benzoic acid or the simplest benzene carboxylic acid. Okay, so now in this case here with the acetylene attached to it, we don't have a benzylic hydrogen to start with. However, this triple bond is oxidizable. We can oxidize that triple bond down to an aldehyde or a ketone. And once we do that, we can oxidize it further to our carboxylic acid. So that's the one special case where you say, oh, but it doesn't have a benzylic hydrogen, but it has an activated carbon because of the multiple pi bonds. Okay. And so once we've actually oxidized it down to a carbonyl, we can actually do oxidation here as well. So in our ethyl benzene, our first oxidation step was actually creating that carbonyl and then oxidizing off our alkyl ketone to give us our benzoic acid or our carboxylic acid in the end. Okay, so we've seen that under these strong oxidizing agents that'll oxidize all these other double bonds and conjugated double bonds down, that we actually don't do anything to the chain. We only do it to, we don't do anything to the benzene ring. We only do it to the side chain, okay? However, there is a way to oxidize down the benzene ring, okay? So, and it takes place in the presence of ozone, okay? So if we use ozone in an acidic condition, in this case, it's acetic acid right here, and the ozone will specifically attack and bind to the benzene system, the pi cloud on the benzene, and then we use peroxide to further oxidize it down. It actually doesn't attack the saturated, this has to be saturated right here, the saturated alkyl chain, because those carbon-hydrogen bonds are not very polar. It actually attacks the benzene ring, and you end up with the alkyl, the saturated alkyl chain, and one of the carbons from the benzene is the carbon in the carboxylic acid. Okay, so this is the only reaction I think we have, I'm double checking my memory, where the benzene ring is the oxidized species. In all the other systems with nitric acid, sulfuric acid, we have substitution reactions. With chromic acid and permanganate, we're oxidizing down the side chain as long as there's either a double bond or a benzylic hydrogen. This is the only one where we leave the alkyl chain unattached and oxidize off the benzene ring. But remember, one of those carbons is from the benzene ring, and that's the carboxylic acid carbon, so that you'll know exactly how many carbons your alkyl chain has. All right, questions on oxidation reactions of benzenes? Okay, we'll move forward then. Okay, so as we started this, we said that benzene was very hard to hydrogenate and that its energy released was less than it should be. And that was what we called our resonance stabilization. Okay, so we can do this, but we have to do it at fairly high temperatures and fairly high pressures to get it to go. Once you get the first addition of hydrogen across the benzene ring, then the dienes created are much quicker in their reduction, and it'll cascade immediately down to the cyclohexane. Okay, so the benzene, the first hydrogenation of the benzene is the slow step. And once you form those dienes, either conjugated or not, they will quickly hydrogenate down to the cyclohexene and then to the cyclohexane. Okay. But again, much higher temperatures than normal for a double bond. Okay. So now, because that's so hard to do and we can't stop it in the reaction, once you form one of those dienes, it's going to go all the way down to cyclohexane. We don't have specificity for stopping it partway through unless we use what we call the dissolving metal reduction. Okay, and in this case, it's similar to the reaction we used with alkynes, where we were taking a metal and ammonia and creating a salt out of it. However, in this case, we're actually using it to form the 1,4-cyclohexadiene. Notice that's the unconjugated form of it, okay? So we end up with that unconjugated form, and one of the reasons that it's unusual is that, you know, it is not the conjugated form, and I don't know why it does this, but we can use it to our advantage, because if we had something like anisole here, so it had a substituent on it, and we didn't want to have that benzene ring anymore, we could use that dissolving metal reduction, and in this case, we're using lithium instead of sodium here. It would form first the ether functionality here, oops, this ether of the cyclohexadiene, and then we could further use an ether clipping mechanism, an acid-based ether clipping mechanism. They would clip it off to give us an alcohol, but that would give us an enol, which would rearrange to give us a ketone. And so we can end up with our ketone, and our ketone just, the other double bond moves with it, and we end up with a conjugated, unsaturated ketone. Okay. So this is actually kind of a useful way to make terpenes and other cycloderivatives out of benzene derivatives. Okay, so we have two different reductions we can do: the catalytic hydrogenation, which is very slow, or the Birch reduction, which allows us to have a functionalized cyclohexadiene. Okay, so now I said before that once we have groups on a system, we're going to have preference for one product ratio or another, right? And so by looking at activation and direction, we can get different isomers just by switching the reagents in their order, okay? So this is going to become very important for getting the exact product you want, okay? So for example, let's say we wanted to make a product that was a nitrobenzene, a nitrobromobenzene, okay? So, but we only wanted a specific isomer, okay? So let's say we wanted the para isomer, okay? So if we have that, let's start it with, if we started with nitrobenzene and we brominated that, nitro is a meta director. We would not get the para product or the ortho product if the nitro group was on there first. So we have to swap the order of addition. So we can start from benzene, and well, it doesn't matter. Benzene has all 6 equivalent spaces, so it doesn't really matter. It's going to go on there, and we're going to have our bromine on there, monobrominated benzene. Okay, our bromine, of course, is a ortho-para director, slightly deactivating, but an ortho-para director. And so when we nitrate it, we get 2 products available to us. We get the ortho product, and we have the para product here. Bromine is not big enough to make the product ratio sway more toward para, so you always get both isomers from the system. But because it's slightly deactivated, and if you're not using extreme heat, you can stop it at 1 nitration, okay? Luckily, these two have different polarities, and you can separate them. And so you can isolate just the para product or just the meta product from the reaction, doing it in that order, okay? Let's say you did it the other way around. You actually nitrated first, okay? So you would end up with a different product because the nitro group is going to meta direct. And that means when you do brominate the system, number one, it's going to be harder to brominate because you have a deactivator. So you're going to have to use a higher temperature. And when it does brominate, it's going to brominate into 1 isomer. You're going to get only the meta isomer because it's a meta director. Doesn't matter which of the meta sites it attacks. It's going to give you monobromination and 1 product. Okay. So does everybody understand that order of addition of substitution is important, and it's directly controlled by ortho-para direction or meta direction? So if you want the meta product, you need your meta director on your ring first. If you want the ortho or para product, you need to have your ortho or para director on the ring first.
Hey, Dr. Irvin, for me at least, I believe you froze when you were discussing the meta direction addition. I don't know if you froze for anybody else.
Okay, well, I can do that again. That's perfectly acceptable. Yeah.
Thank you.
So if we look at the other system, oh, somebody else had that same problem. Okay, good. All right, so let's say we want the meta director. We want the meta isomer. So in that case, we want to make sure the meta director is on the ring first, because remember, benzene has no specificity. Those are 6 even things, so it doesn't matter where we put the first group on. It's going to give us this, and now this is directing us to the meta position. So it could be this position or this position, it doesn't matter. If we monobrominate, those positions are equivalent and gives us one product, the meta isomer. Okay, does that, did that cover everywhere I was frozen?
Yes, sir, thank you.
So, all right, so look at your final product. Look at which of those things are ortho and meta directors or para directors, and that's going to tell you which order to use your reagents. Okay, so let's talk about another way to direct things. Okay, so oops, come on. Oh no, where do you go? So what if you want to do something where you want the meta isomer, but the thing you put on there is so deactivating that you can't get the next reaction to happen, okay? So, sorry for spinning through the slides so quickly. Okay, so we can actually control our product by taking into account the fact that a precursor to the desired functional group is actually a director for another position, okay? So for example, carboxylic acids have a carbonyl compound on them, therefore they are meta directors, okay? So if you want to produce a product that has a substituent that's meta to a carboxylic acid, you can just do a direct reaction on the carboxylic acid, okay? So in the case of the lower half of the screen right here, if we want the meta substituted benzoic acid here, the benzoic acid's a meta director, so we only have to chlorinate that, maybe use a little extra heat because it's a deactivator, but it's going to meta direct. And we're going to end up with our chloro on the meta position and the meta position only, okay? However, if we wanted the parachloro or the orthochloro benzoic acid, we're never going to get that chlorine to substitute on the benzoic acid in those positions. So let's flip it around. What precursor to a carboxylic acid we have? Well, we know we can oxidize down alkyl groups. So we can actually do a chlorination with a benzene with an alkyl group on it first, okay? Now, if we have a methyl group, right, it's not very big, so we're going to get some para, but we're also going to get some ortho, okay? So we have to think about that this is not going to be the highest yielding reaction. But once we have this, we have these benzylic hydrogens, and therefore we can oxidize those benzylic hydrogens off and get us to our carboxylic acid. What could we do to boost our yield of the para derivative here as opposed to the meta or the ortho derivative? Okay, so we can't put a T-butyl group there forcing it all 100% to the para position because we lose that benzylic hydrogen. But we could put an isopropyl group on here or have a long chain alkyl group off of here. As long as we have one benzylic hydrogen, we can do the oxidation to get us to the correct isomer of our parabenzoic acid. Okay, so in the reactions with alcohol chapter, we introduced the topic of protecting groups. And in benzene systems, we might end up with having the same thing, especially if we have something like an amine, because amines react and don't let you do um, like Friedel-Crafts reactions on them. Okay. So in this example, what we want to do is we want to make para-nitroaniline. Okay. So para-nitroaniline. So if we have a nitro group on there, that's let's see, that's a meta director. So we probably don't want to put the amine on second, but the amine is easily oxidized by the nitric acid. So we can't just nitrate aniline directly, okay? So we have to find some way to make that nitrogen less reactive toward oxidation, okay? And what we are going to choose to do is we're going to try to make the nitrogen a little less susceptible to oxidation by protecting it as, in this case, the acid amide, okay? So that's, we take acetyl chloride or an acid chloride of acetic acid, and we take away one of those hydrogens and make that amide structure here. This amide structure is more stable to oxidation, and therefore, but it's still an activator because it still has that lone pair on it right up here. So then we can actually nitrate it. Now notice this protecting group is kind of big, and so it's, you know, flipping around like this because of that free rotation on that sigma bond. So it's actually going to direct to most of the product is going to be in that para position, and only a little bit of that product is going to be in the ortho position. And that has everything to do with the size of this protecting group. If you wanted to really drive it home, you might be able to use the T-butyl group here to really make sure you have almost all of it, the desired product here. Now, once you formed your nitrated product here, you still want to get back your amine. So you have to go through a hydrolysis step and hydrolyze off this acetyl group, taking it to a carboxylic acid and regenerating your amine compound. Okay. So this is another case where you can't get there directly by the product you wanted because of reactivity. So in the first case, it was the the chlorobenzoic acid, where it would be deactivator or a methyl director, but we wanted the para isomer. Here, we're using the amine still as a para director, but we don't want it to be oxidized in the system, and therefore we can protect it as the amide and regenerate it with hydrolysis. Okay. So the next thing I want to talk about is how to protect a group using sulfonic acids. Remember, when we talked about the sulfonation of the ring, we said that was the only one of these reactions that was reversible, and we could possibly use it as a protecting group to protect a specific location. Okay, and so I'm going to show you how to do that on this next slide. Don't go all the way over. All right. Okay, so for example, let's start again with that acid aniline we used before, which is the acetate amide of the aniline right there. And let's say we wanted actually to make, instead of the para-nitro compound, we actually wanted to force it to the ortho position, okay? Remember, because of, darn it. Because of the size of this amide group and the spinning around, that we only got a minor portion of it was our ortho derivative. Let's say we wanted that to be our major portion of the reaction, okay? So we have to do something with that para position to block it so the nitration does not occur there. Okay. So what we're going to do is we're going to use that same protecting group, that acetate, the acid amide group here, to keep the nitrogen from oxidizing. But what we're going to do is we're going to do our addition of our sulfonic acid first. Okay. So our sulfonic acid is a deactivator. However, it's also a meta director. Okay. So we have an ortho para director at the top, which is directing it here and here, and the para position is now blocked. And now we have our sulfonic acid directing meta here and here. So that means the only place we're going to nitrate is in this meta position, is in the meta to the sulfonic acid position, or the ortho to the acid anilide. Okay? And then if we were to go ahead and undergo a removal of that sulfonic acid, turns out that same condition, that acidic water, is the same conditions we use to remove the sulfonic acid group as clip off this acid aniline group, yielding our amine. Notice we have a second step here. We have to, because we have an acid there, the acid would have protonated the amine here, and so the base here at the end is actually to deprotonate the amine to give us our free group. All right, now, so we're using the sulfonic acid group to block. However, the sulfonic acid group is a deactivator, and the acid aniline's a little bit big because remember, we didn't get that ortho substitution before, which accounts for our slightly lower yield than the previous reaction because it's sterically hindered, so the reaction goes slower, and it's slightly deactivated from before because of the sulfonic acid group. So our yields aren't great, but we have exactly one isomer, and we've directed exactly where it's going to go by using the protecting group of the sulfonic acid and the protecting group of the amide of acetic acid. We use two protecting groups to get the exact product we want. Okay, that is the end of the chapter 15. Are there any questions? We're right at 1 o'clock, so let me go ahead and stop video recording and then answer questions, and then we'll come back.